Are you curious about the workings of a capacitor? This small but significant device, tucked away inside countless electronic instruments we use daily, showcases the brilliance of scientific creativity. This tiny powerhouse is simpler than it seems, and unraveling its inner workings is an intriguing quest. Let's embark on a journey to uncover the inner workings of this integral electronic component. Consider the capacitor as two parallel conducting plates termed as plate 1 and plate 2, separated by a dielectric. The dielectric is essentially an insulator. Its purpose is to prevent a direct electrical link between the two plates while permitting an electrostatic field to permeate. Imagine attaching a battery across the capacitor. What happens next is quite fascinating. Each plate of the capacitor assumes a charge. Plate 1 establishes a connection with the battery's positive terminal, and on the other hand, plate 2 connects with the negative terminal. This connection gives rise to a potential difference across the capacitor. As the battery's current tries to cross from plate 1 to plate 2, the dielectric, the insulating material, intervenes. It interrupts the current, preventing it from passing from one plate to the other. Yet, an electric field starts to develop across the capacitor. This electric field is the crux of how a capacitor operates. As the time progresses, plate 1 begins accumulating positive charge from the battery, while plate 2 starts collecting negative charge. This integral step, known as the charging process, involves the accumulation of opposing charges on each plate. The charging time, as it's referred to, period during which the capacitor collects the maximum amount of charge relative to its capacitance, and what happens when you disconnect the battery. Fascinatingly, the capacitor retains its charge for some duration, effectively turning into a storehouse of electrical energy. Now, connect the two ends of the capacitor to a load, and a current will flow from the positive plate to the negative plate through the load until all charges disappear. This action is referred to as the discharging phase. The length of this phase, the time it takes for the capacitors to empty itself of all accumulated charges, is referred to as the discharging time. It's an important concept when considering the functionality of capacitors in any electrical circuit, whether it's DC or AC. In the instance of a DC circuit, there are some essential dynamics to understand. A capacitor initially allows the electric current to pass through until it reaches its full charging potential. At this point, the capacitor has reached full capacity and does not permit additional current to flow. The reason behind this lies in the principle of potential difference. Once charged to its maximum, the potential difference between the battery supplying the current and the capacitor becomes zero, hence stopping further current flow. The scenario with an AC circuit is slightly different. In this case, the capacitor undergoes a continuous cycle of charging and discharging, provoked by the alternating nature of the AC. The polarity of the plates changes in accordance with the positive and negative halves of the AC voltage. During the positive half, one plate accumulates a positive charge and the other a negative charge. When the negative half cycle is in play, the charges on the plates reverse, with no actual flow of electrons between the plates. So, in essence, a capacitor is a device that stores electrical energy in an electrostatic field. It charges and discharges alternately in AC circuits. If you found this concise explanation helpful, kindly give this video a thumbs up, share with your friends, and subscribe for more such enlightening content. We encourage you to leave your queries in the comment section. Explore and learn more every day. Thanks for tuning in.